Dr. Sillen, I'm tired of this dull routine. I wish we could put our knowledge to good use.
Hold on, Perry. I'm getting a call.
Dr. Sillen, a deadly microbe, azamium, has been released into the Texas water supply and could kill all of the Texas turtles if it isn't stopped. We need your expertise to solve this issue at once.
Mr. Governor, I'll be right on it. Perry, we need to deploy the exact amount of this universal antibacterial into the water supply immediately.
But Dr. Sillen, first we need to determine the exact amount of microbes in the water. How can we track the growth of the bacterium in the water supply?
There is one way, absorbance.
But Dr. Sillen, how would that help us right now?
Well, you see, Perry, light is a part of the electromagnetic spectrum, which means it behaves like a wave when entering space. However, the energy of the wave is absorbed at specific locations, the same way particles are absorbed. This unique nature of light is described as wave-particle duality. One of light's many primary properties is intensity, which is the power of light transferred per area. We can use light's properties to measure the absorption or the energy of a wave that is transferred to matter as light passes through. The amplitude of the wave decreases as its energy is absorbed by a medium. If all of wave's energy is absorbed, the medium is opaque, like how water becomes opaque with depth. Other particles too, like bacteria, further decrease energy. This is described by the Beer-Lambert's law, or Beer's law. The absorptive capacity of a dissolved substance depends on its concentration in a substance. IZ is the intensity of light at a certain depth, while IO is the intensity of light at the surface. X is the light extinction coefficient, and Z is depth. I've gathered a sample from the water supply. We can put it through my spectrophotometer, which will measure the absorbance of the sample, which can be used to determine the number of microbes.
Oh no, the spectrophotometer won't turn on. It must be broken. What are we going to do?
This is an unforeseen hurdle, Perry. I'm not sure if this will work, but perhaps we can try using fluorescence instead.
But how would that be any different than absorbance?
Well, Perry, fluorescence occurs when an object spontaneously emits a burst of radiation after exciting radiation is extinguished. This burst of radiation is re-emitted energy converted from absorbed radiation, only happening after absorbance has already occurred. This can be seen in this graph. Fluorescence can only occur at lower frequencies than the incident radiation, as some energy is always dissipated into its surroundings. Water can accept high amounts of energy, having the quenching effect on fluorescence. This means that wavelengths will always be longer, often resulting in visible light of oranges and greens. Certain biological molecules fluoresce strongly, such as chlorophylls. Their fluorescence can be measured using a machine, like a fluorometer. I've gathered another sample from the water supply. We can use my fluorometer to quantify the chlorophyll, which we can use to estimate how much azambium is in the water.
Oh no, it didn't work. Why?
Rats! Azambium must not have chlorophyll, so fluorescence won't work. I don't know what to do since fluorescence won't work and our spectrophotometer isn't working.
Wait a second, Dr. Sillen. The spectrophotometer wasn't plugged in.
Brilliant, Perry. This should solve that hurdle. Let's analyze the water sample. Finally, we know how much exactly azambium is in the water, and now we can deploy this antibacterial to save the Texas turtles in the nick of time.
Congrats, Dr. Sillen. Your work saved the day. Those turtles look pretty safe to me.
I couldn't have done it without you, for my knowledge of fluorescence and absorbance.